For my final video, I elected to make a video about semiconductors and transistors, considering the current age that we live in. First, I want to go over the history of semiconductors. The first transistor was made of germanium, and it was made in 1947 at Bell's lab by John Bardeen and William Brattain. However, germanium is sensitive to changes in heat, so they were quick to find a replacement for it. The first silicon transistor was made in 1954 by Morris Tannenbaum. However, it was not very effective, and it was too costly to make, even compared to the very costly germanium transistors at the time. The first MOSFET transistor, which utilized silicon oxide effects in order to create a transistor, was invented in 1959 by Mohammed Atalla and Dawan Kong, all three manufactured at Bell Labs, which is AT&T Bell's lab. First, when discussing semiconductors, we have to note their properties, specifically electrical properties. Comparing them to the two classes of materials already seen thus far, they have a low energy gap of less than 2 electron volts compared to insulators, hence their name semiconductors. There are two types of conductivity that we're interested in: pure or intrinsic, and doped or impure and extrinsic in regards to the concentration of semiconducting material. To understand how extrinsic semiconductors work, we must first understand how conductivity of intrinsic semiconductors works. The conductivity of intrinsic semiconductors is as follows. It is the intrinsic carrier concentration, which is equal to the number of electrons or holes times the electric charge of an electron times the sum of the hole mobility plus the electron mobility. Now that we understand that, we must understand that there are two different types of semiconductor that are extrinsic: N-type and P-type, which are both created when impurities are added to pure silicon or germanium or other semiconducting materials. Normally, the concentration of these impurities only has to be about 1 in 1 trillion atoms, which is not that much for extrinsic semiconductivity. N-type semiconductors are those that have doped, or having had impurities added, if you've never seen the word doped before, in use with semiconductors, with group 5A elements, which are compounds such as phosphorus, arsenic, etc. These are defined by excessive quantities of electrons, since group 5A elements have 5 valence electrons, thus having one free electron that is weakly held by the 5A atom. This allows it to freely explore the crystal lattice that it's in, allowing it to dominate the conductivity equation. In this case, conductivity is equal to the number of electrons times the charge of the electron times the electron mobility. In contrast with N-type semiconductors, P-type semiconductors are doped with group 3 elements such as boron, just as it was for N-type semiconductors. P-type semiconductors have a defect that prevents them from fully bonding with other silicon atoms. They have only 3 electrons to hand out. So there is one hole left behind, which can be thought of as a positive charge moving. This positive charge takes very little to energize other electrons to it, so thus it can be thought of as having a large quantity of holes compared to electrons. And just as it was for N-type semiconductors, P-type semiconductor conductivity is dominated by hole mobility. Just as it was for N-type semiconductors, P-type semiconductors conductivity's equation is the number of holes times the charge of the electron times the hole mobility. Conductivity is dependent on temperature as that determines the lattice length and the amount of energy that electrons have to try to be conductive. It allows for higher conductivity. However, increasing the temperature too much can cause semiconductors to become intrinsic, as electrons will be allowed to, as electrons or holes will be allowed to be conductive. Germanium especially is more sensitive to changes in temperature, which is what led to the rise in silicon and the downfall of germanium in modern technology, except for in certain pieces of equipment. For example, in sound equipment, sometimes they contain germanium transistors for amplification purposes, and they are frozen before shows to get better sound. However, freezing them can cause complete failure of semiconductivity, as there will not be enough energy to move electrons around. Obviously, if you increase impurities too much, it'll decrease mobility. There is a maximum amount of conductivity that you can extract, and that is at low concentration. Now, semiconductors are used in 3 different types of electrical devices that I will be discussing here today. These are diodes, junction transistors, and MOSFET transistors. Diodes are the simplest type of semiconductor device. They are an N-type silicon and a P-type silicon joined together. When electrical force is applied through the negative side or the N side, it allows current to flow through the diode, as the holes and electrons will meet and annihilate each other, creating a depletion zone. This allows electricity to flow through. If it is applied to the opposite side, then there is nothing happening in the middle, and no electrical flow is being provided unless you provide a large amount of voltage through the middle. This is important to understand for our next thing, the junction transistor. A junction transistor is a diode with an extra piece of silicon added on. It can be either NPN or PNP, in which case it works on either electrons in NPN or holes in PNP. There are 2 voltage sources which both share common ground through the base. The input voltage goes through the emitter and to the base, creating a depletion zone between the emitter and the base. There is either a positive or negative charge in the collector, as the collector's electrons are forced to one side. This causes the electrons or holes in the emitter to jump straight to the other side to the collector, creating a large output voltage and also allowing for logic gate functions. This is the basics of how a transistor works. A MOSFET transistor works by varying the conductivity of the material that it's made of. This requires less amperage to occur to create a depletion zone, which makes it ideal for use in computers. Recalling back to Ohm's law, P is equal to IV. This means that less power is required to perform logic gate operations. This type of transistor is not the most effective in amplifier circuits, however. To manufacture semiconductor devices, they have to be made on the same piece of silicon. They cannot be made of 2 different crystals of silicon. To accomplish this, a gigantic crystal of silicon called a silicon boule is created. It is then cut and then impurities are added to it, layer by layer. For my 3D model, I made a transistor component for a breadboard circuit because I think that it's kind of interesting, breadboard circuits. My sources for the pictures are Material Science and Engineering and Introduction, 10th edition, our textbook. Thank you.